Well, thanks so much to the meeting organizers for inviting me to give this talk. It's a great privilege to be here and give this presentation to all of you. So what I want to do is talk about some work we've been doing using passive source seismic data to image a variety of basins in Africa. And this work is part of a larger initiative called AfricaArray, which I'll tell you a little bit more about in just a second. But before I get going, I'd like to acknowledge the large number of people that have been involved in all of this work over the years, students, postdocs, and research affiliates. I'm not going to go through all the names here, but I do want to acknowledge all the help I've had from a wide variety of students and postdocs and other faculty over the years. And this work has also been in collaboration with many colleagues in various African countries. And again, there's too many people to mention, so I've just listed all the countries here that we've been working in over the last 10 years as part of AfricaArray. So there's individuals in various universities and geological surveys, other government organizations in these countries that have been part of AfricaArray and helped with the research that we've accomplished. So when I give a talk about Africa, I always like to start by showing a slide and making some general remarks about the continent. First of all, Africa is huge. It's a huge continent. You can fit China, the US, including Alaska, and Europe, plus a bunch of other countries inside the continent. A lot of people, especially in the US, don't realize how big the continent is. And so when we look at African Earth features, basins, rift valleys, and so forth, it's important to keep in mind the immensity of the continent. Also, I'd like to point out that the topography of the continent is very different in northern and central Africa versus eastern and southern Africa. So this is a colored DEM of Africa. The oranges and red areas are areas over a kilometer in elevation. And so, as we all know, there's the uplifted areas of the Ethiopian Plateau, the East African Plateau, and the Southern African Plateau that constitute a very large topographic anomaly on our planet. And this part of Africa topographically is much different than what we see across the rest of Africa. And when it comes to understanding basin structure and looking at the topography, especially in eastern and southern Africa, this large topographic feature here is directly related to what is happening in the deep mantle. And I don't want to say too much about the deep mantle in this talk, but I do want to make sure that everyone is aware that what is happening tectonically across eastern and southern Africa is directly coupled to the largest seismic anomaly in Earth's mantle, the so-called African superplume. This is a P-wave tomographic image of the mantle going from near the core mantle boundary to the surface along this profile, AA prime, so through southern Africa, eastern Africa, Ethiopia, and into the Arabian Peninsula. And those geographic areas are shown here on top of this plot. So this is the upper part of the mantle beneath southern Africa and so forth. So the African superplume is this large seismic anomaly. It's manifest as a low wave speed anomaly where the hot colors here where the waves are traveling slower than we would expect, indicating that the mantle is hotter than normal. And this structure originates at the core mantle boundary beneath southern Africa here and makes its way up through the mid-mantle and then turns in the upper mantle beneath East Africa here, and this structure extends all the way through East Africa, Ethiopia, and into the Arabian Peninsula. So I like to refer to this structure as a superplume structure because it is to first order a thermal structure, but it is also a chemical structure as well, particularly in the lower mantle where this structure has an anomalous chemistry. So this feature is rising through the African mantle. It crosses into the upper mantle beneath Zambia, somewhere right around there, and then turns in the upper mantle. Now, from a variety of different studies we've done, we've argued that the structure is actually rising through the mantle and then turning, as is shown in this cross-section here. So this image here I've taken and turned on its edge and put some arrows on here to show the direction of flow that we think is occurring in this structure. So the structure is coming up through the mantle here, turning in the mid-mantle here, and then moving to the north and around the center of the Tanzania Crate, the Archean Craton that sits in the middle of East Africa here. It's moving around it on either side of the Craton structure and heading to the north through Ethiopia and the Arabian Peninsula. So first order structure, and if we want to understand what's been happening with basin development through the Mesozoic and the Cenozoic, we have to understand the structure because the structure is probably long-lived. It probably originated under Pangea, and the structure has been there through the Mesozoic and the Cenozoic, affecting basin structure throughout eastern and southern Africa. Okay, so enough about the mantle. What I want to do in this talk is show you some results from studies of 3 basins we've been working on using passive source seismic data that's collected as part of AfricaArray. The first study that I'm going to talk about is a study of the Congo Basin, the Greater Congo Basin, or Cuvette Centrale, sitting here in the central part of Africa. Then I'll shift on and move and talk about the basins along the western side of Madagascar. And then I'll end by saying a few things about this area and the Mozambique plain in southern Mozambique. So Africa hosts a variety of different kinds of basins as shown here in the key, different color codes. And so I'll be looking at just 3 of the basins in some detail in this talk. And then at the end I'll also mention some perspective work looking at some of the Kru basins in this part of southern Africa. So the data we've been using for all these studies come from this initiative called AfricaArray. So let me just say a few things about AfricaArray. We started the initiative in 2004 with 3 founding partners: Penn State University, the University of the Witwatersrand in Johannesburg, South Africa, or WITS for short, and the Council for Geoscience, also referred to as the Geological Survey of South Africa. And the initiative started as an intervention to rebuild the geophysics program at the University of the Witwatersrand. Through the 90s, they had a geophysics program that had gone into decline, and in the early 2000s, they wanted to rejuvenate the geophysics program. So the original ideas for AfricaArray came about in a discussion I had with various faculty at WITS about how we could rebuild the program. And one of the key components we decided to put in place was a seismic network to record earthquakes across southern and eastern Africa and feed the data into their graduate program at WITS for providing new data sets for students to work on. So as the years have gone on, there's been a number of components that have come together to make AfricaArray what it is today, and they're listed here. There's a network that includes seismic, GPS, and weather sensors. I'll show you a map in a second. There's a number of undergraduate and graduate education programs and research programs here in the U.S. And also at a variety of African universities. We have programs focused on enhancing diversity in the geosciences here in the U.S. as well as in Africa. And all of this is been done through fundraising for projects. So we don't have any core funding for what we do. Everything has been done on a project-by-project basis. Now, just some numbers to give you a snapshot of what we've accomplished over the last 10 years. We have a public-private funding partnership with contributors from a number of government organizations. The National Science Foundation here, the National Research Foundation in South Africa are the 2 largest contributors from the government. The founding partners have put a fair bit of resources into AfricaArray, and then we have a significant number of corporate sponsors that have funded projects over the years. In terms of students completing degrees, WITS University is on the British system, so they teach geophysics as a 4th-year degree, so BSc honors degree. We've had over 60 students graduate, 19 masters, 12 PhDs, and we've supported 13 postdocs. And in our diversity program here in the U.S., we've supported over 103 minority students. Networks, I'll show you our map in a second of the permanent observatories. We've also operated many temporary seismic networks over the years. The partnership base supporting all this is broken out by different kinds of institutions here, universities in Africa, elsewhere, US, Europe, Australia, government organizations, and so forth. And here are the number of companies that have provided support over the years. And we've had endorsements from 6 academic and industry societies as well. So quite a large partnership base that has supported this endeavor over the last 10 years. So here's the permanent network of observatories that we've developed, spanning mainly eastern and southern Africa. The triangles are color-coded with the different kinds of sensors. So the blue ones have co-located seismic, GPS, and weather sensors, and you can see the other colors here. The white are seismic-only stations. So through eastern and southern Africa, a few stations or observatories in West Africa and a couple in Madagascar. So out of these, 50 have seismic sensors, 24 have GPS receivers and weather sensors. We record continuously. Our data recovery has been between 70 to 80% over the years. The data is archived at IRIS and UNAVCO. These are NSF-supported academic consortium to support seismic and geodetic research. And most of the data is downloaded periodically. These are standalone stations. Some of them are networked. We're trying to improve the uptime and get more stations online, but many of them still are remote stations, and someone has to go and download the data every so often. Couple of photos showing what the stations look like. This is a picture of the station here in Ghana. It's a little bit dark, sorry about that, but it's a building here. In the bottom of this building is a concrete pier that's on bedrock, and there's been a variety of seismometers deployed over the years, going all the way back to the early 1970s. For those of you who are seismologists, these are old Benioff seismometers from 1960s era seismometers. This is a new broadband sensor that we installed at this station. This is a station in western Zambia here, and it was a vault that was built on a dam. The dam was never completed, so it sat there for 30-some years, and we came back and we were able to put our equipment on a concrete pier in the middle of this building, and solar panels on the top, and there's a GPS antenna and our weather sensor. So that's what the infrastructure looks like for these observatories. Now, the temporary stations we've operated in various places. This is a map that shows stations throughout eastern Africa, extending down into Zambia over the years. Most of these are stations that we've deployed as part of AfricaArray, but some of these are older stations that the CRISP project deployed in the late 1980s in Kenya. So these data have been critical for imaging basin structure and crust and upper mantle structure across eastern Africa. And these are temporary stations where we dig a pit into the ground, put a seismometer on a concrete pier, and then we cover the equipment with drums, bury it, and then we have a solar panel at the surface for power. So the data we collect looks like this. This is a recording of a broadband, of a seismogram recorded with one of our broadband sensors. So we're looking at seismic data that's recorded at a high fidelity between 10 hertz and greater than 120-second period. These are mainly large earthquakes that happen around the globe. This is an example of a 5.5 magnitude earthquake in Indonesia that was recorded on a station in Kenya. This is the vertical component of ground motion shown on the top, and you can see the P wave, the S wave, followed by the surface wave. In this case, it's the Rayleigh wave. We can take our seismogram and we can filter it. And what's shown here are bandpass filters at various periods going from 10 seconds all the way to 125 seconds. And you can see the surface wave here is a dispersed wave train, and as we go to longer and longer periods, the wavelengths are longer, so they sample deeper in the earth, and the wave packet, the wave energy arrives sooner. So I'm going to be talking a fair bit about surface waves and some of the imaging that we've been doing in these basins. So I wanted to show this and point out that as we go to longer periods, again, we sample deeper in the earth, and these longer wavelength waves have a greater sensitivity at depth. So over here is a plot depth. You don't need to worry about this axis here, other than this is a graph that shows the sensitivity of the surface waves to different depths. So say a 50-second surface wave has its peak sensitivity to structure, say, between 50 and 100 kilometer depth, whereas a 125-second surface wave, so this guy down here, say, has peak sensitivity at here 150 to 200 kilometer depth. So the longer the wavelength, the longer the period, the deeper we're seeing into the earth. Okay, so let's move on, talk about some basins. The first one is the Cuvette Centrale, or the Congo Basin, and not to confuse this with the Congo Basin offshore West Africa. This is the basin that sits here in the middle interior of Central Africa. That's the outline of the basin. It's an immense basin. It's roughly half the size of the lower 48 states, 10% of the African continent, about 1.2 million square kilometers. The geology is, well, we know at the surface what the outcrops are, but very little is known about the deep structure of the basin. So looking at the geology here, the surface geology, most of the outcrops that is been mapped is Cretaceous in age. So that's the green area here. The yellow area here is the tertiary and quaternary sediments sitting on top of the Cretaceous section. And then peripheral to the Cretaceous section are some older sections going back through the Karoo and then all the way back into the the late Paleozoic and into the Neoproterozoic at the base of the basin. What little work has been done on the basin comes from 4 wells that were drilled. This one here, M, S, G, and D. I'll just point those out because I'll refer to those later. Those are wells that were drilled in the 70s and 80s. And a number of old seismic profiles that were collected in the 70s and 80s. This one here, a couple in this area and this area here. Now the interpretation of the main basin structure from this limited data set is that there is a structural high that runs through the basin that goes through here. It's called the Kiri High here, and the Laconia High in this part of the basin. And I'll come back to those structures in just a little bit. So the section again goes from the Neoproterozoic all the way through up into the Cenozoic. And in terms of source rocks in the basin, there's potentially some source rocks down here in the older part of the section, but the most promising source rocks are these 2 formations here, the Stanleyville and Loia formation, that are late Jurassic, early Cretaceous in age. However, the work that's been done on these so far from limited well cuttings and also from outcrop samples suggests that they are immature where they've been sampled. So I'll also come back to that point in a little bit. The deepest well is 4.5 kilometers deep. Sediments, however, could be up to 9 kilometers thick based on the measured sections in outcrop, projecting those into the basin. So the structural high that runs through the middle of the basin that I just mentioned here has been interpreted in 2 ways. The first way comes from papers by Daly, 1992 and 1991. And based on the limited seismic data, for example, this line here, which is, this line runs right through there. He suggested that there was this large structural high here in the middle of the basin called the Kiri High, and that it was bounded by thrust faults on either side. This seismic line is located there, so that's right there across that part of the high. And he argued, Daly argued, and his co-authors argued that the basement high was related to 2 episodes of compression, one in the early Paleozoic, and another one in mid-Jurassic from far-field stress transmission. But let me back up a second and say that the basin originally probably started in the Neoproterozoic as a rift basin. So the faults in the center part of the basin were originally normal faults. And then from the formation of Gondwana in the early Paleozoic, you have collision around the margins of Africa, so all the continents were assembled into Gondwana. And you have stress transmission into the middle part of the continent, causing reactivation of these normal faults and thrusting. And then you have a second phase of reactivation of these faults during the late Paleozoic, where you have the formation of the Karoo Basin here and the Cape Fold Belt to the south of Africa with this large subduction system to the south. Again, you get the far-field stress transmission into the interior part of Africa, causing reactivation of these thrust faults and continued development of this structural high in the middle of the basin. So that's Daly et al.'s story. Kadima et al. In 2011 published a reinterpretation of a number of these seismic lines and argued that much of the evidence for structural high could be accounted for with salt tectonics. So these wells did encounter layers of salt in the basin. And so this is a reinterpretation of this line here, R13, right there in the middle of this high. And there's the big salt pillow that he put into his interpretation with a basement that is more or less flat here without any disruption of the basement. So he argued that in some places there could be a uplift of the basement, but much of the structural high here is actually has been caused by salt movement in the basin. So how can we contribute to the story and understanding of the first order basin structure? Well, we have been developing a surface wave tomography across the entire continent over the last few years. So let me tell you about that, and then I'll explain how it helps us understand the basin. So what's shown here is a map. All the blue dots on here are earthquakes, and they're all recorded. These earthquakes are recorded at our stations in Africa. Those stations are not shown on here, but each one of these faint blue lines represents a path from an earthquake from an earthquake to a station. So for each one of these paths, we have a set of data that looks like this. So our seismogram that we can filter at different periods. And so for these data sets, we can then measure the velocity at which this wave packet or this group of energy is arriving, and that's shown over here. So what's shown here is the group velocity versus period. So at each period, we can measure the velocity at which this energy is arriving at that station. Then we can take all these paths. There's over 40,000 paths in here where we have these kinds of measurements. And at each period, this is for 20 seconds, so each period we can use that data and we can image how the speeds, the group velocities, vary across the continent at that given period. So here's for 20 seconds showing how the group velocities vary in speed across the area. Now there's lots of stuff on this map. I don't want to dwell on all these different areas that are shaded here, but do want to point out that in the area of the Cuvette Centrale here, there's some areas that where the group velocities are lower in places where they are higher. So we can do this at every single period, and then we can take those group velocities and we can do another inversion to actually map in shear wave velocity structure as a function of depth. So what's shown here is a map of the variation in the shear wave speeds across the Cuvette Centrale and the area around it at depths of 1, 2, 3, and 4 kilometers. And the color bars are the same for all of these figures here. The margin of the basin, the Cretaceous outcrop is shown here, the zero contour. And those 4 wells I pointed out here are shown quite faintly with white, one there, one there, one there, and one there. And then the red lines show those structural highs that were interpreted. So what we see is that in the northern part of the basin, there is a low wave speed region down here at 2.6 or so kilometers per second, and also one in the southern part of the basin. And that pattern persists at 2 kilometers. We see it at 3 kilometers, and we also see it at 4 kilometers. So now let's take some slices, some depth slices through this model and look at what we see. So here is that same map at 4 kilometer depth, and we'll look at these east-west profiles first. This is AA prime, BB prime, and CC prime here. So this is a little bit hard to see, but it looks like the letters got cut off also. This is going from a Mac to a PC. Sorry about that. This is AA prime, BB prime, and CC prime, and these are the wells. There should be labels on these wells here showing them. And what we can see is a low wave speed region here under the basin. The X's are the edges of the basins there, right there. So we see this low wave speed area. And this well here, none of these wells penetrated basement. This well is the deepest one at 4.5 kilometers. It didn't get all the way to the basement. And so we have interpreted or tried to interpret the depth of the sedimentary section by taking the 3.3 kilometer per second contour, it's shown by the faint red line here, as the sediment basement contact below this well. So that's drawn on here, and it's drawn on this map also. So that's what it looks like if we go east-west across the basin. Now let's go north-south. So AA prime, this is AA prime, BB prime in the middle, and CC prime. And again, the wells are shown here, and that faint dashed red line is what we would call the basement sediment basin basement interface. So what we see quite clearly on these north-south profiles is that there is this large structural high in the middle of the basin running right through here. You see it very clearly there. You see it very clearly there, and there's also a hint of it on that line too. And these velocities here at upwards of 3.5 kilometers per second are much too fast to be salt. In terms of looking at the first order basin structure of the Cuvette Centrale, I think we can make some pretty firm conclusions. So again, just remind you that we have these two competing interpretations, salt tectonics versus thrusting, to create this structural high in the middle of the basin. And from these cross sections, again, we see this basement uplift. So clearly, the structural high is primarily a basement uplift. There could be some salt tectonics at work here, but we think to first order, we have a very large basement uplift. And the previous interpretation had that basement uplift going northeast-southwest. And if we look at our map here, we think it's more oriented east-west or maybe even going southwest to northeast like this across this area. And that basement high then divides the basin into two main depot centers. So there's two depot centers that haven't been previously recognized, one in the northern part of the basin. So again, here is the outline of the Cretaceous. There's a major depot center in the north, one in the south with this large structural high in the middle, and that's shown again on these two north-south cross sections. So this is in the north and this one is in the south. And if we look at the depth, our estimated depth of basement here, it puts us at 9 to 10 kilometers of sediment beneath the center part of these depot centers. Also, the implications then for the source rocks, especially the Jurassic and Cretaceous source rocks, again, they were sampled on the edge of the basin in outcrops and in these wells, and looking at the position of the wells with respect to the depot centers would suggest that the source rocks in the center part of these depot centers may be sufficiently deep that they could be mature. The samples, again, that were taken in these wells up in the Jurassic and Cretaceous section appeared to be immature. So in terms of basement structure then, just to recap, clearly a basement high here that separates the basin. So first order basin architecture, basement high with two large depot centers, 8 to 9 kilometers of sediment. In the middle of these depot centers, perhaps source rocks that could be mature. Okay, so that's the first basin. I want to move on to the next one. I look at Madagascar. So here's the geologic map of Madagascar. Major basins along the the western side of Madagascar with the Precambrian core shown in white and brown and green up here, this area. This is all Precambrian. The basins, as probably many of you know better than I do, started as Karoo basins. So here's the stratigraphic column with the explanation down here for this column. So the section going back to the Carboniferous to the Permian Triassic, this is all Karoo. Sediments in the bottom of the basins prior to the rifting of the separation of Madagascar from East Africa. Then we get into the Upper Jurassic, Lower Cretaceous. This is the main rift phase. And then we get further up in the Upper Cretaceous into the Tertiary. Then you get the marginal sag and passive margin deposition in these basins as Madagascar was moving away from East Africa. So what we've done in this study, been doing many things, is using data from all of these seismic stations. All these triangles are seismic stations that we've been deployed in Madagascar for various periods of time. And using data in a variety of ways to look at basin structure as well as crust and upper mantle structure. And the results I want to show you is from PhD work by one of our students at Wits University. I'm not going to try to pronounce his name here. He's from Madagascar. His first name is Finitra. That's easier. So one of the studies he's done to look at basin structure is to use what we call receiver functions. And receiver functions are simply a way to process the seismic data, the P wave in particular, to pull out converted phases from boundaries beneath the receiver. So what's shown here is a surface with a 3-component seismic station and the Moho discontinuity as a major discontinuity in the Earth, but this could be any discontinuity. And we have an incident P wave on this discontinuity, and some of the P energy gets converted to S energy. And then we record at the station both the P energy plus the P to S converted energy. So all that energy arrives. Here is the P wave, and just after the P wave, in the first 10 to 20 seconds or so after the P wave. And so in order to isolate those converted phases, we do some processing, which I'm not going to go into any detail. We remove the source effects, we remove the instrument effects, and we end up with what we call a receiver function. And in cartoon form, it looks like this, where we have an arrival, which is the direct P wave. Then we have P to S conversions from any discontinuities underneath the receiver. And then we have reverberations from those conversions bouncing between that discontinuity and the surface. So those are the waves that are bouncing up and down in the crust. So this discontinuity again could be the moho, it could be the sediment-basement interface, it could be a mid-crustal interface, it could be deeper in the earth, in the mantle. So the receiver functions are then generated using large seismograms from large earthquakes. So here's our network in Madagascar, and this shows the distribution of all the large earthquakes that we've processed. And we end up with waves that look like this, or wave trains that look like this, where this is the P wave. These are all different receiver functions from different earthquakes. So that's the direct P wave. Right there is the P to S conversion from the moho, right there. And then back here are these reverberations. So this is what a receiver function looks like, and we can then model that for structure underneath the receivers. And we can do this in a variety of different ways, and again, I'm not going to go through the detail of the processing, but I want to just give you a sense of how we can do this. We can do simple forward modeling of the receiver functions. So the gray trace here is the observed receiver function, and the black trace is the modeled receiver function. So we can simply take a shear wave velocity structure here of the crust. So here's a basin, low velocity sediment basin at the surface, and there's the moho there at 22 kilometers. And we can create a synthetic seismogram and try to match our observed seismogram. And in this particular case, we get a pretty good match to these first couple of arrivals. This is the P wave. That arrival there is the P to S conversion from the sediment basement interface. And then this is the P to S conversion from the moho down here. We can also take our receiver functions and we can go through a grid search procedure where we define a parameter space, in this case a VP-VS ratio versus moho depth, and we can search through the space to find the models or the combination of parameters that best fit the arrival of the PS time on all these receiver functions, and then the reverberations that follow. So I don't think you could probably see that from the back, but with this process we try to match the arrival times of these different waves in this model space. And we can end up then defining what the moho depth is, shown here is H, 36 kilometers in this case, and then our VP-VS ratio, which is 1.72. We can also take the waveforms, the receiver functions, and put them into a formal waveform inversion, which is illustrated over here. So again, synthetics and the data shown here for the receiver functions. And in this inversion, we can also add in additional information that helps constrain the velocity structure of the Earth. In this case, we've used phase velocities from Rayleigh waves instead of group velocities. And we combine these two, and we end up with a model, a 1D model of the Earth underneath our receiver for showing the shear wave velocity structure as a function of depth. So depth here, 0 going down. There's the moho at 35 kilometers, and we can actually see how the shear wave speeds vary as a function of depth in the Earth. So putting this together, what do we actually find out about the basins in Madagascar? Again, we have these three major basins with Kru and younger sediments. So what's shown here is results for showing what the crustal thickness looks like across the entire island. And so the Precambrian area, here again in white and tan and green, this whole area here, we find pretty typical Precambrian crustal thicknesses on the order of 35 plus. On average here, it's maybe like 38 to 40 kilometers across all of the Precambrian in this part of the island. Now under the basins here, we find much thinner crust. It goes from, on the edge of the basins here, it goes from 30 kilometers and then all the way down, and the thinnest crust is up here in the north at 18 kilometers. So if we consider that all of this area prior to rifting was probably on the order of 35 to 40 kilometers, and we look at the thicknesses today underneath of the crust underneath these basins of down here on 20 to 25, even 18 kilometers up here, it indicates that from the rifting event that the crust under these basins has been thinned by 15 to 20 kilometers. So there's been a tremendous amount of crustal thinning under these basins. So what else can we learn about the basins from this kind of imaging? Well, we can map the thickness of the sediments. That's what's shown here. in colors, and this boundary, this gray boundary here, just to orient you again, is the basement, the contact between the basins and the Precambrian basement to the east. So what we find is that where we have stations, the thickest sediment is over here along the coast, the western side, and it's up to 8 kilometers thick, and the sedimentary section thins more or less uniformly towards the east, towards the Precambrian basement. So west to east thinning. And then we also find that in the north here, where we have actually the thinnest crust, this is really quite interesting, we actually have lesser amounts of sediment, so only a few kilometers of sediment in the north. So the basin thickness, then the sediments are thinning from west to east, and they're also thinning from south to north in this case. That was a bit of a surprise to us. We thought we would find thicker sediments where we have the thinnest crust being the most extension and possibly the deepest basins. So other things we can learn about these basins and the structure related to these basins, we can look at the average shear velocity of the crust, shown here in colors, going from 3 to 3.8 kilometers per second. And again, the area, the Precambrian basement here is fast. The average shear velocity of the crust is upwards of 3.7 kilometers per second. And in the basins to the east, to the west, here, the average shear velocity of the crust is much slower, all the way down to 3 kilometers per second. And that's because if we just break out the velocity of the sediments themselves, I put that down here. In the west, where the sediments are the thickest here, the average shear wave velocity is 2.4 kilometers per second, and then it increases to about 2.7 kilometers per second as we move to the east. And that makes sense in terms of the structure, because as we approach the Precambrian over here, we actually get older Karoo sediments that are coming up to the surface and outcropping. So the sediments to the east are a little bit faster than they are on average over to the west. Okay, so the last example I want to show here is from the coastal plain of Madagascar. And this is work that Mercedes Gaynor did with me this last year for a senior thesis at Penn State. So we're looking at this area. Here's Mozambique. We're looking at the coastal plain of Mozambique, this area here that is covered by quaternary sediments. And this area has been of interest for a long time because it's critical for reconstructions of Gondwana. And so taking this picture here from this paper by Leenweber and Jokart, this area right in here, this area here is critical for understanding how tight you can reconstruct the continents back in against Africa and what happens in terms of the rifting story in this part of the opening of the southern part of this basin. So a number of authors have argued that the crust under this part of the coastal plain is actually oceanic, and it was crust that developed during the opening of Gondwana, the earliest rifting stage. It's again taking another paper by Leenweber and Jokart here. They use this map here showing the gravity. It's a gravity map of this part of Africa. Here's the coastline right there. This is the Mozambique coastal plain here. And in this paper, they argue that everywhere from this monocline right here that goes through here, coming in this direction, all of this area was floored by thickened oceanic crust. And so if that's the case, then you can reconstruct and put Antarctica back in here and have this whole area open up as the rifting progressed. So we were curious about this, whether or not our seismic data would confirm whether this area had oceanic crust or whether it's actually stretched continental crust. So what Mercedes did was to look at some surface waves again. So I'll just remind you that we have a surface wave that we record, and it's a dispersed wave trend. We go to longer periods, we see deeper in the earth. And this is a crazy busy figure here. There's just two things I want to point out. This is velocity in kilometers per second in period here on a log scale. And there's two curves that are important here. The red curve that I've highlighted here is the group velocity for an oceanic Rayleigh wave, and you can see that at 10 seconds here it's low and then it rises quickly, and by the time you get to 20 seconds it's up here at 4 kilometers per second, very fast. And that's because it's sampling the fast oceanic crust. The continental Rayleigh wave, shown in yellow here, is different. It's a little more complicated. Again, going from 10 seconds up here to 20 to 30 seconds, it's much slower than the Rayleigh wave going through an oceanic area. So we should be able to map out this difference. If the crust underneath that part of the Mozambique plain is oceanic in nature, then we should be seeing a curve that looks something like that. So we deployed a number of stations in Mozambique, shown here as part of an AfricaArray project. And then we also had a couple stations in South Africa that we were able to use for this study. And we were able to record a number of small earthquakes. These are magnitude 4 earthquakes shown by stars in this part of Mozambique here, and recorded at these stations here in Mozambique, as well as these 2 stations in South Africa. And so for each one of these events, we were able to measure the group velocities. So again, here's the seismogram, and now we're only looking at a few seconds of data because these are small earthquakes and the travel paths are quite short. So here's what the data, the raw seismogram looks like, the vertical component of ground motion. This is filtered from 1 to 10 seconds, 10 to 20 seconds, and 20 to 30 seconds. And again, you can see the dispersed wave train. So we can take the data, again, like we did before, we can map out the changes in the group velocity as a function of period. In this case, we go from 2 just to 20 seconds, and you can see the results there. So what does that look like? Well, for all these paths, all the data are shown here. Again, this is a busy figure, but I just want to point out a couple things. The green line here again is the group velocity curve for an average oceanic crust covered with oceanic sediments. So again, you go from 10 to 15 seconds, you go up to very fast group velocities of 3.5 to 4 kilometers per second. If we take that same oceanic crust and now we put 9 kilometers of continental sediments on it, this is what the curve looks like. So at these periods here, it's faster, but you still get up here to 15 seconds, you're up here at very fast group velocities. Now for all of these paths through this area, we can see in this period range of 10 to 25 to 30 seconds, you can see that all of the group velocities are well below what we would expect for oceanic crust. And so pretty clear indication that this crust here is not oceanic. It's got to be continental. And these wave speeds are actually very, very slow. So let me look at just one curve here for this station right there, because it goes east, more or less east-west from the earthquakes there to the coastal area across the coastal plain. And this particular station has the slowest group velocities. Even at periods of 25 to 30 seconds, we're below 2.5 kilometers per second. So we've done some very simple modeling of these group velocities using a grid search again. So we create a simple crustal model with a sedimentary layer above a crystalline basement, and then we can compute synthetic group velocity curves and try to match our data. So what's shown over here are this is the data, the group velocity curves in black, and the red lines are all synthetic curves for different models that we tried, where we took a sedimentary package here and a crustal package, and we varied the velocities for the crust, the Precambrian crystalline crust, and the sediments sitting on top of that. And then we also changed the thickness of the crust. So this is the moho depth, and then this is the thickness of the sedimentary layer itself. So we tried to find the combination, very simple sedimentary package over crystalline basement that would fit our data over here. And the results are pretty rough, but what they indicate quite clearly is that we can't have crust that's oceanic in nature. So on the order of 7 to 10 kilometers, the crust has got to be up here at 25 kilometers or thicker. Now, we don't have tight constraints on how thick the crust is, but it's clearly the results of the crust has to be greater than 25 kilometers thick, and the velocity of the crust is at 3.4 kilometers per second. So this is clearly not oceanic crust that we're dealing with in this area of the Mozambique plain. Also, the sedimentary velocities are low here at 2.4, 2.5 kilometers per second, and the sedimentary package is actually quite thick, upwards of 10 to 15 kilometers, in order to match these very, very low group velocities in this period range of 15 to 25 seconds in particular. So, no oceanic crust, and a very, very thick sedimentary section underneath that part of the coastal plain. So just to recap, again, in this area here, we don't see any evidence for any kind of an oceanic crust under the Mozambique plain. It's got to be continental crust. It's probably very stretched. It's attenuated. It's thinned. We don't know exactly how thin it is. We have a lot more work to do on that. It's a really interesting problem. But in terms of reconstructing the opening of this part or these basins here, this area right there is got to be part of the African continent. Okay, to finish up here, I just want to tell you a little bit about some future work that we have planned. This is a map that shows Karoo basins in eastern and southern Africa. So the darker colored areas here are areas of known Karoo deposits, and then the lighter brown areas are areas where there's inferred Karoo that has younger cover over it. So what we want to do is to use our group velocity tomography of Africa to try to image some of these basins right here, and particularly the ones that are covered. And those two basins there in particular are perspective, because if we look at the results we have so far from our group, our surface wave tomography, we can see that there's a low wave speed structure that's associated with that area there. This area is all covered by Kalahari sand, so we don't really know anything about the Karoo and that part of Africa. And this structure right there corresponds with that area there, also covered by Kalahari sands. So we right now have networks of temporary stations that we've deployed across northern Namibia and across all of Botswana, and we're recording earthquakes. And so we hope we will be able to take that data and start improving our coverage, array coverage across this part of Africa, and improve then these surface wave group velocity maps, and be able to hopefully get better images of these basins across this part of Africa. So that's coming soon, hopefully. Okay, the last thing I want to do is put in a plug here for a new Seismic Research Centre that we started last year at Wits University. This was done with support from Shell. It's a reflection seismic data processing and imaging center looking at basins, and we're looking at crystalline Precambrian basins as well as Phanerozoic sedimentary basins that are prospective for petroleum exploration. Musa Manzi is the director. He's a new faculty member at Wits University, and he has been busy acquiring legacy data sets from a number of companies, and those data sets are shown here. This is the Aeromag map of southern Africa. Really hard to see on here, but this is the border between Botswana and South Africa running through here like that. So all of these black lines are seismic lines seismic data that he has been able to acquire and archive and use for student research. Most of it's in southern Africa. We've been able to get some data from Botswana. There's also some offshore 3D seismic data sets that Musa has been able to gain access to. So we think there's a great future here for acquiring or getting access to legacy data sets, particularly old 2D seismic data sets from African basins. We'd like to be able to preserve those data, archive them properly, and then make them make them available for use in the future for students and postdocs and faculty working in Africa. And I think in particular there's great potential for merging limited interpretations from select 2D lines. For example, these areas here in Botswana, if we go back and combine that with our surface wave mapping of those structures, putting those two kinds of data sets together, I think we can learn a lot about many basins in Africa that we don't know much about at the moment. So with that, I'll stop. Thank you.
On behalf of the HGS and the audience, thank you very much for your talk. Mr. Nyblade, and here's the award we have, a Speaker's Award from the HGS. It's a piece of the rattlesnake limestone.
Great, thank you very much.
Thank you very much. Okay, if you have any more questions for the speaker, you can come up and I'm sure he will answer them. For everybody else, the meeting's adjourned. Thank you.